first video, I told you that there were nearly an octillion atoms and 7 pounds of salt. You may have wondered where that number came from. Yes, I calculated it myself, and yes, I had to use Avogadro's number to get there. But so far, we've only learned one way to use the mole, to put a bundle of numbers on atoms or molecules or apples. I told you that the number of atoms or moles don't mean anything to us until we attach a mass to them. So how did I connect the mass of salt to the number of atoms? Well, it turns out there's actually 2 ways we can approach the mole, and they come from the 2 ways we measure substances in the lab, by weighing out the substance and by counting the components that the substance contains. What do I mean? Well, let's take a minute and think about the last time you purchased produce from the grocery store, apples, oranges, etc. There's 2 possible ways you can purchase them: by charging a price per piece of produce, like Trader Joe's does, or by charging a price per pound of the produce, or kilogram. Here, most grocery stores other than Trader Joe's charge by the pound because there can be a big variation in the size of a fruit or vegetable. We can take the same approaches with atoms. The method that we use on the macro scale is weighing things out. E.g., you measure out the salt with dashes, shakes, teaspoons, or a food scale rather than counting out individual salt grains. The counting method works well for things that are on the macro scale, like cookies or apples, but not for chemicals, because individual units are far too small for us to see, even with a super powerful microscope. By packing individual units that are too small for us to see, like we use dozens to talk about a large quantity of cookies, we give ourselves the ability to count atoms too. In fact, you can call the mole the chemist's counting number. So where does mass come in? Remember back when we talked about what an atomic mass unit was? To measure the mass of atoms, we set our unit arbitrarily to be almost equal to the mass of a proton, giving us a point to enter convert between the mass of the atom and the number of particles in the atom, or a connection between mass and counting numbers. The number we get for the mass number of an atom is a good estimate of the actual mass of the atom in atomic mass units. We use the same hack when counting atoms themselves within a mass of an element or compound. What scientists did is they designated a conversion factor between the mass of the substance and the number of particles that made it up to be equal to the number of carbon-12 atoms and 12 grams of carbon-12. Let me repeat that. The number of carbon-12 atoms and 12 grams of carbon-12, which has a mass of 12 AMU or 12 grams per mole. That's a lot of 12s. But what does it mean? A mole is a number of atoms that are present when you have a chunk of your element or compound where the number associated with the mass in grams matches the mass of an individual element in AMU. This also happens to be the amount that contains Avogadro's number's worth of atoms. So for carbon-12, when we muster up 12 grams of pure carbon-12, so we have 12 grams of an atom with an atomic mass of 12 AMU, we have 6.022 times 10 to the 23rd atoms. It turns out that this relationship holds up for every other single element and therefore any combination of elements. To illustrate this concept, let's take a look at another element, fluorine, which has an atomic mass of 18.9984 AMU. If we were to go out into the world and pick up a sample of fluorine that was exactly equal to 18.9984 grams, it would contain 1 mole of fluorine. So that number we see on the bottom of an element's box on the periodic table actually has 2 meanings. It is the mass of an individual atom in AMU, and it is the mass of 1 mole of the element in grams. We call this quantity the molar mass, or the mass in grams of 1 mole of an element, or a molecule, or a compound. The units of molar mass are grams per mole, or G/mol, and we can find the molar mass of an atom by looking at a periodic table, or for a compound by adding together the masses of all the constituent atoms. Mind blown. Let's try calculating it another way. Let's say you have a pure silver ring that weighs 75.2 grams. How many moles of silver solid, are contained in this ring? The conversion factor here would be the atomic mass of silver. Note, since we assume we use the element as it occurs in nature, unless told otherwise, we use the molar mass given on the elements block for the average atomic mass of the element. We look at the periodic table, we find 107.87, which is the mass of a single silver atom in AMU, and the mass of a mole of silver in grams per mole. We start off with 75.2 grams of silver. We want moles of silver. So what we do is we put grams on the bottom and moles on the top. Moles are our larger quantities, so we put the one with moles, then we put the molar mass in grams on the bottom. Grams cancel, we end up with 75.2 divided by 107.87 to give us 0.7 moles. So, going back to the mole map, if we have the mass of an element in grams, we can arrive at the moles of an element by dividing by the molar mass. We can go the opposite direction too and multiply the moles by the molar mass to give us grams. Wait a second. Remember when we said we didn't have a frame of reference for what 0.7 moles of silver was? Well, now we do. 0.7 moles of silver is equal to 75 grams of silver, which also happens to contain 3.2 times 10 to the 23rd atoms. And there you have the beauty of the mole. If we have a counting number, a number of atoms, Avogadro's number takes us to moles. If we have mass, the molar mass also takes us to moles. So Avogadro's number allows us to interconvert between number of atoms and the mass of element via the moles of the element. Can we do the same thing with compounds? Let's find out. Let's say that we have 173.5 grams of silver sulfide, which is the dark smudge that appears when silver is exposed to air for long periods of time. How many moles of silver sulfide do we have? Quick hint, you can find the molar mass of a compound by adding together the molar mass of all the individual atoms. Pause and try it yourself. If you got 107.87 times 2 plus 32.06 for 247.80 grams per mole, you are correct. So we start with 173.5 grams of silver sulfide. We multiply 1 mole divided by 247.87 grams, grams cancel, and we get 0.7 moles. It worked again. So if we have a particular molecule or compound, we can divide by the molar mass of the compound to get us the moles of compound. We can go the opposite direction too. But wait a hot minute. 0.7 moles of silver was 75 grams. But 0.7 moles of silver sulfide was 173.5 grams? Why is there a difference? Atoms weigh different amounts, and the more atoms you have in a formula unit, so 3 atoms in silver sulfide versus 1 atom in elemental silver, the mass of the same number of units will get bigger. Therefore, the molar mass, and by extension, the mass of a single mole, gets bigger with increasing size and number of atoms. So we've looked at both silver and silver sulfide here, and we've seen that both contain 0.7 moles of their formula unit. Do they contain the same amount of silver? The same number of silver atoms specifically? We don't have the tools to figure that out quite yet, but we'll find out in the next video, stoichiometry.